In this video, I'll talk about colligative properties of strong electrolytes. So if we look at the definition of colligative properties, they should not depend on the nature or type of the solute. So let's say if we put 1 mole sucrose in water or 1 mole some other chemicals in water, the melting point depression and boiling point elevation should be the same. The osmotic pressure caused by adding solutes into water should be the same. So what's the difference here? Why do we want to emphasize the colligative properties of strong electrolytes? Now imagine if we put 1 mole sucrose in 1 liter of water. And how many sucrose molecules do we have in water? 6 times 10 to the power 23. Sucrose molecules. Now what if I put 1 mole sodium chloride in the same amount of water? Well, now we have twice the solute particles. We have 1 mole sodium plus and 1 mole chlorine minus. This is because strong electrolytes dissolve in water and produce solvated cations and solvated anions. So that's the difference. Look, colligative properties only depend on the mole fractions of water if we're talking about aqueous solution, right? But then if you add, let's say, 1 mole of sucrose into 9 moles of water, the mole fraction of water is going to be 0.9. So again, 9 moles of water divided by 1 plus 9. So it's 0.9 mole fraction. The mole fraction of water becomes 0.9. What if you add 1 mole sodium chloride into 9 moles of water? Okay, look, the mole fraction of water, again, it's the number of moles of water divided by the total number of moles of all particles. So still you have 9 on the top. But what's on the bottom? It's 9 mole water plus 1 mole sodium plus 1 mole chlorine minus. So we are looking at 9 divided by 11. And that's roughly 0.81. So again, if you add 1 mole sucrose into 9 moles of water, the mole fraction of water becomes 0.9. But if you add 2 moles, if you add 1 mole of sodium chloride into water, you get 2 moles of ions. All right, and then the mole fraction of water is 9 over 11. 9 over 11 is 0.81. So there is a difference. Now, what if you add, for example, aluminum chloride? That's AlCl3, aluminum Cl3. And then 1 mole aluminum chloride decomposes into 1 mole aluminum ions and 3 moles of chlorine ions. So you create 4 moles of particles. In that case, if you add 1 mole of aluminum chloride into 9 moles of water, on top you still have 9 moles of water, but on the bottom it's going to be 9 plus 4. You get 13 moles of particles. 9 moles water molecules, 1 mole aluminum, and 3 moles of chloride. So 9 over 13. 9 over 13 is a little bit lower than 0.7. So again, I want to emphasize this. Strong electrolytes decompose in water. Okay, and 1 mole strong electrolytes produces more than 1 mole particles in water. Right? So again, for sodium chloride, 1 mole sodium chloride can produce 2 moles of particles. And now this time, if we're talking about the boiling point elevation, freezing point depression, or the computation of this osmotic pressure, we have to include this factor 2 here for sodium chloride. This M is the molarity of sodium chloride, but each sodium chloride produces 2 ions. Here, here. And over here, this N is the number of moles of sodium chloride. But what about the number of moles of the ions? It's 2N instead of 1N. All right, so you use these 3 equations instead. And this 2 is the number of particles produced by just one this formula unit. This is called the Van't Hoff factor. Okay. So now practice problem. Let's say 1 mole of sodium chloride is dissolved in 1 kilogram of water and form 1 liter of solution. This is a rough estimate. It's probably going to be a little bit different from 1 liter, but again, we're just trying to estimate the numbers here. What's the boiling point and melting point of water? What's the osmotic pressure of this solution compared to pure water? So in this case, we still do similar calculations, but when we calculate the boiling point elevation, we need to include this 2 here, and this is the molality of sodium chloride. It's just 1 mole sodium chloride per kilogram of solvent, but again, we need to multiply that by 2 to emphasize that 1 sodium chloride now becomes 1 sodium plus and 1 chlorine minus. All right, and then this case of B, we can look it up. It's 0.5. The result is 1.02 Kelvin. And then also we can do similar calculations over here to get the freezing point depression, which is 3.72. So again, we have this factor here. The freezing point depression caused by sodium chloride, 1 mole sodium chloride is twice that caused by 1 mole sucrose, because sucrose does not decompose in water. And then we get the new melting point and boiling point of water. It's going to be 101.02 degrees Celsius and negative 3.72 degrees Celsius, respectively. What about the osmotic pressure of this solution? Again, we use pi v equals nRT. Well, this can be lowercase pi or uppercase pi, depending on which book you're reading. And then we use pi v equals nRT. But over here, this is the Van't Hoff factor. We just use nRT over V over here. Again, Van't Hoff factor. So I'm going to type it up. Van't Hoff factor. All right. So I'll put it in the middle. In some book, the notation is I. Again, in this case, I is 2. So we just compute this. Again, I think I made a mistake here. It's actually 5 million pascals. So it's actually 50 bars. So if you put 1 mole of sodium chloride into water, you're going to create a huge osmotic pressure of roughly 50 bars or 50 ATMs. That's huge. All right. Okay, by the way, you can use this kind of salt solution to kill people too. Okay, by creating such high osmotic pressure. One more practice problem. Let's use 0.5 moles of iron chloride, and we dissolve that into 1 kilogram of water, and we form 1 liter solution. What's the boiling point and melting point of water now? What's the osmotic pressure of this solution in comparison with pure water? The result actually is exactly the same as 1 mole. So 0.5 mole of iron chloride is exactly the same as 1 mole sodium chloride regarding the boiling point elevation, melting point depression, or osmotic pressure. Because again, 1 mole sodium chloride creates 2 moles of ions, and 0.5 moles of iron chloride creates also 2 moles of ions. We don't care about the nature, the type of the ions. We just care about the numbers. 0.5 moles of this ionic compound will produce 0.5 moles of this iron and also 1.5 moles of chloride. So together 2 moles of particles. Exactly same as the number of particles produced by dissolving 1 mole sodium chloride in the same amount of water. Alright, so really it's the same result. Again, you need to introduce this Van Hoff factor here, I. So this I is twice that of sodium chloride, but I give you just 1/2 of the concentration of this ionic compound, so they cancel in the end. The melting point depression and melting point, the boiling point elevation and melting point depression are exactly the same. So again, but unfortunately I made the same mistake here, numerical mistake here, so maybe I should fix all this. Alright, we're done. How about osmotic pressure? Again, another mistake here. It's actually 5 million pascals. It's huge pressure and 50 bars or roughly 50 atm. And try to place those red blood cells in just 0.5 molar iron chloride or 1 molar sodium chloride. This time you will see the water will flow from the inside of the cell to the outside a salt solution. All right.